Hi, my name's Reagan, and this is What's in Water. Oh, I don't know what. Okay, so sometimes when drinking a glass of water, it can taste different than drinking bottled water. But why is that? It's because there's different compounds in the water. But how can one tell if a glass of water was contaminated versus a regular glass of water? Because when looking at the two, they look exactly the same. They're both clear. So the objective of this lab was to determine the identity of the contaminant in drinking water. So in this presentation, I will be talking about how I came to the conclusion about the identity of my contaminant in my sample. So before testing, we had to fill out different tables that we would later compare our results to. So when filling out these tables, we would use them to cross-compare our results back to them to help us identify the identity of the unknown contaminant. So the thermoscientific spectrophotometer was used for the IR spectra, and the EFT60 was used for the NMR spectra. So the IR uses the absorption of photons to create this wavelength that tells you the different functional groups. So at the bottom of each peak, there will be a number, and that corresponds with the functional group. The NMR does the same thing with the absorption of photons, but it tells you information about the hydrogen. So it tells you the different types, how many there are, and the relative ratio in between them. And that was given by the Department of Chemistry in our lab manual. So this was the table that was given in our lab manual, and you can see with the IR absorption peaks, the different functional groups, and the range of absorption that corresponds with each. You can see there are 3 different arrows, but we'll come back to that later. So this was my sample, sample 25141. As you can see, this is the IR spectra for that particular sample with the unknown contaminant in it. And then I cross-compared it with this table that was given. And so I used all of these numbers and I cross-compared them to see if any matched with a functional group. And you can see that there are 3 circled, so those corresponded with the table and led to the OH range, the CH single bond range, and then the CCl bond range. Circled are the 3. Next, here is the table for the IR spectrum of the 15 different molecules. So using both those 2 tables and the 3 different ranges, I looked at the possible ranges for the molecules, and you can see that I decided to go with ones that had OH and CH only and not the CCl. With this, I determined that the CCl was weak and needed to be strong, so I decided to eliminate that from my possible choices. So the possible choices based off of my IR spectra for sample 25141 was methanol, ethanol, T-butanol, and T-propanol. Next was the NMR spectrum for sample 25141. You can see there are 2 peaks. This number faintly says 9 and this one says 1. So the ratio between these 2 is a 9-to-1 ratio with 2 peaks. Then we had to fill out this table for the Nmr spectroscopy of the 15 different molecules that could possibly be our contaminant. And you cross-compared your results from this table, so the 9-to-1 ratio with the 2 peaks, to find a possible molecule. And as seen, those combinations led to T-butanol, and only T-butanol. There was no other option. That was close. So next was the process of elimination to determine which molecule was my contaminant. So going back to IR spectrum results, you can see there were 3 different peaks with these different bonds. And then going back to this table, there were 4 different molecule combinations. So based off of these results, I still could not eliminate further, and I was only left with these. Now, cross-comparing, we had to use the NMR spectra results. As previously stated, the 9-to-1 ratio with 2 peaks only led to the combination of T-butanol, and T-butanol was present in both. So that is how I concluded that the contaminant in my sample of drinking water had to be T-butanol because it was present in both the IR spectra and the NMR spectra. So the conclusion was that the identity of the unknown in my sample was T-butanol, and the objective of this lab was to identify that. So using the different tables of the 15 different molecules and my results from the sample, I was able to cross-compare my findings of the IR spectra and the NMR spectra back to those tables to draw a conclusion about it. And that is how I got my conclusion that it was T-butanol. So overall, T-butanol, we had to cross-compare it to the effects it had on humans and in nature. So T-butanol in drinking water, although it hasn't been tested on humans yet, it has been tested on male and female lab rats, and it was shown that there was an increase of kidney failure and cancer. So like I said, even though it hasn't been tested on humans yet, it can be concluded that since it has this effect on lab rats, it could possibly have this effect on humans, and therefore it's negative and harmful towards humans. But however, in the environment, T-butanol doesn't have a significant impact, and it can even be beneficial. So in the environment, T-butanol is biodegradable, and it does not build up in soil, roots. It isn't really traced back in animals, and it isn't in the water. Even though it is in the water, it doesn't have an impact to the water, if that makes sense. So overall in the environment, T-butanol really has no effect. And these are my references. As previously stated, there were a lot of given tables from the Department of Chemistry in our lab manual. And then for the information about the lab rats and T-butanol, that was from the Minnesota Department of Health. And the information about the environment was from the University of Ashland.